How's it going, folks? Welcome to probably one of the most important lessons that we're going to go through this entire year. Okay, we're going to be working with the fundamental theorem of calculus. Yes, it is as important as you may think it sounds. Okay. So there are two main pieces in calculus that we've talked about this year. The first revolves around derivatives, and the second will revolve around definite integrals. I know definite integrals are still fairly new to us, but they are very important and they are a key component of calculus. It's actually a really nice fact, though, that the derivative and a definite integral are actually inverses of each other, similar to how multiplication and division are. So similarly to multiplication and division, you just do the opposite to cancel it out. Derivatives and definite integrals are the same exact way. A derivative is just the rate of change or slope, which is the rate of change, which is the change of y over the change of x. And your definite integral is going to be your area, which is just your change of y multiplied by your change of x. So moving forward here. The fundamental theorem of calculus, abbreviated by FTC, states that if a function f is continuous on the closed interval ab, and f is the antiderivative of f on the same interval, then the integral is going from a to b of f of x dx is going to be the antiderivative of b minus the antiderivative of a. Now this may sound like a bunch of mumbo jumbo, but trust me, this is going to make your life significantly easier. We're essentially bypassing that whole sigma notation thing. Okay, so guidelines for using the fundamental theorem of calculus. So the first thing is that there has to be an antiderivative. So provided a function has an antiderivative, using the fundamental theorem of calculus allows us to find the area without using a limit of a sum. Okay, so that's the first thing that is very key. There has to be an antiderivative that exists. The second is going to be that we're going to use this notation. Okay, now this notation is very important. Okay, so we have the integral from a to b of f of x dx. It's going to be equal to the antiderivative from a to b. Now we're going to denote this as this straight line after that. That means that we're going to take, dang it, I wrote that wrong. Of course, I knew I was going to do something wrong here. It's f of b minus f of a. Okay, so we're going to have the integral of f of x dx from a to b. It's going to be the antiderivative of a to b. So it's going to be equal to the antiderivative of b minus the antiderivative of a. Okay, you may be asking, well, what about our plus c, our constant of integration? Now, this is actually not necessary to include because, as you can see, it worked out here. So we get the antiderivative plus c from a to b. So we have antiderivative b plus c minus the antiderivative of a plus c. You'll see that this subtraction is distributed to both of them. So those c's end up being canceled out, and we're just left with the antiderivative of b minus the antiderivative of a. Okay, we're going to go ahead and look at a specific example here. So we're going to evaluate this definite integral. So we're going to first take the integral. Okay, we're going to find that antiderivative. So our antiderivative of x cubed is going to be x to the fourth over 4. And remember, we're going to use our nice notation. It's just going to be a line right after it. We're going to write the boundaries. So 1 to 3. So from here, we're going to use our value of b, which is going to be 3. So we're going to have 3 to the fourth power over 4. And we're going to subtract f of a. And that's going to be substituting in our lower boundary. So we're going to have 1 to the fourth over 4. And we're just going to simplify here. We're going to be left with 81 over 4, and we're going to subtract 1 over 4 to be left with 80 over 4, which simplifies to be 20. Okay, so we get to skip all of those sigma notations, hoo-ha, all that kind of stuff. We're just going to go ahead and use the fundamental theorem of calculus. It's going to make our life way, way easier. Okay, we've got two more examples we're going to do right here. The first, we're going to evaluate the definite integral. So we have the integral from 1 to 2 of x squared minus 3 dx. So the first thing we're going to want to go ahead and do is take the antiderivative. So our antiderivative in this case, the antiderivative of x squared is going to be x cubed over 3. And our antiderivative of negative 3 is going to be negative 3x. And we're going to take all of this from the bounds of 1 to 2. From here, we're going to find f of b. Remember, so we're finding the antiderivative of b minus the antiderivative of a. So we're going to substitute 2 in first. So we have 2 cubed over 3 minus 3 times 2. Okay, that's f of b. This whole thing is f of b. And we're going to subtract f of a. Now, f of a, we're going to substitute our lower bound, which is going to be 1. We have 1 cubed over 3 minus 3 times 1. And again, this is going to be f of a. And we're going to simplify this. This is going to leave us with 8 over 3 minus 6. And we're going to subtract 1 over 3 minus 3. Now, it's really important to keep our parentheses here because this is typically where people make mistakes. Okay, you're going to have to trust me on this. Please keep your parentheses. Okay, from here, we're going to go ahead and we can distribute this negative if we want, but we end up with negative 2 over 3 once you simplify all of your fractions. Okay, so again, a much easier way to solve as opposed to using our sigma notation. Okay, you should feel a little upset because I taught you that sigma notation and this is so much easier. Okay, this is like when we were learning about derivatives and we had to first learn our derivatives by the limit notation first, and then we learned the power rule. Okay, this can be treated as the same way. We first learned it using sigma notation. Now we are using the fundamental theorem of calculus. Okay, so we're going to look at one more direct example here. So we're going to evaluate the definite integral. Now this one's a little bit different because we have an absolute value. So there really are two functions here. It's really important to first know what your function is doing. So we're going to have a function, the absolute value of 2x minus 1. So we have f of x is absolute value of 2x minus 1. So our function here is actually going to look something like this. Okay, this is a rough sketch, but it's going to be something like that, where this value is going to be x equals 1/2. So that's where we have a shift from two different functions. Okay, again, absolute value of 2x minus 1 is really negative 2x minus 1 when x is less than 1/2, and it's going to be positive 2x minus 1 when x is greater than or equal to 1/2. So we're going to work with two separate integrals here. Okay, remember from yesterday's lesson we talked about how integrals can be split up. This is going to be rewritten. We're going to rewrite it as the integral from 0 to 1/2 of negative 2x minus 1 dx. And we're going to add the integral of 1/2 to 2 of 2x minus 1 dx. Okay, again, we're going to be able to do that because there are really two separate functions here. Okay, this is one function and this is our other, the left side and then the right side where we have that vertex. Okay, our bounds are chosen from where that value changes. So from here, we're going to go ahead and integrate both of these. We're going to go ahead and get that this first one is going to be negative x squared plus x, and we're going to have the bounds from 0 to 1/2, and we're going to add the integral over here. So we have x squared minus x from the bounds of 1/2 to 2. Okay, now we're going to substitute our values of f of a and f of b. Now in this case, we're going to have two sets of that. We have an f of a f of b minus f of a here, and we're going to add f of b minus f of a for this piece as well. So we're going to go ahead and do that. When we plug our values in, f of b in this case is negative 1/4 plus 1/2. F of a is going to be 0 plus 0. We're going to then add our f of b for the second piece, which is going to be 4 minus 2. We're going to subtract our f of a, which is 1/4 minus 1/2. Okay, once you simplify all of those things, let's see, in this piece, we're left with 1/4. This is 0 plus 2, and then we're going to subtract negative 1/2. I'm sorry, negative 1/4. So it's plus and a positive there. We're going to go ahead and get that this should be, oops, what did I do wrong? What did I do wrong? 1/4, that's negative 1/4, that's right. 2. Oh, whoops, that's a negative. That's why. Okay, sorry about that. Negative 1/4 plus 1/2 gives us 1/4. So all of this ends up adding to be 5/2, or 2 and 1/2. Okay, moving on, we've got one more example working with the fundamental theorem of calculus. Okay, so we're going to find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2. It's going to be bound by the x-axis and also be bound by the vertical lines x equals 0 and x equals 2. Now, those vertical lines are going to be important because those are going to tell us where our lower and upper bounds are. First thing we're going to want to do is we're going to write out our definite integral. So we have 0 to 2, and our function is 2x squared minus 3x plus 2, and we cannot forget our dx. First thing we're going to do is find our antiderivative. So we're going to have 2x cubed over 3 minus 3x squared over 2 plus 2x, and it's going to be on the bounds from 0 to 2. Now we're going to find our f of b. So our f of b is going to be, we're going to substitute 2 in. So we have 2 times 2 cubed over 3, subtract 3 times 2 squared over 2, and we're going to add 2 times 2. So this is our f of b. We're going to subtract our f of a. Okay, so we're going to substitute our values of 0 in. So we have 2 times 0 cubed over 3 minus 3 times 0 squared over 2 plus 2 times 0. Okay, as we can see, all of these pieces have 0, so we're just left with the left side, which is going to give us 16 over 3 minus 6 plus 4, which is going to simplify to be 10 over 3. Okay, so outside of the fundamental theorem of calculus, we do have two other things that we're going to talk about today. The first is going to be the mean value theorem. Now, this should sound familiar. The mean value theorem stated that if there was a derivative within a function that was continuous, there was another derivative in that same interval that is going to be the same. Now, the mean value theorem when working with integration is a little bit different. If our function f is continuous on the closed interval from a to b, then there exists a value c in which the closed interval ab such that the integral of ab of f of x dx is equal to f of c times b minus a. Again, that's a lot of words, can be a little confusing. I'm going to draw a picture to make it look a little bit nicer. Okay, so essentially what we're going to have, we have our axes here, and we're going to graph a line. Okay, we're going to have some kind of function. Let's say it looks something like this. Say this is our value of A, this is our value of B. Now we know if we take the integral from A to B, we're going to find the area that exists under this line. Okay, so the red is the area under that line. What this states is that there is some value, let's use a different color, use blue. There is some value of C that will make a rectangle here such that this area, the blue area, is the same exact thing as the red area. So this is going to be true for every single function regardless. If you want to see a proof, there is a proof in section 7.4. Okay, if you want to look at it, it's there. You're going to have to take my word for it. What this f of c is just the height. Okay, so this is f of c, and then b minus a is the width of this rectangle. So as you can see, this is just the area of a rectangle. So there is some value of c within this bounds of a to b such that the area of this rectangle will be exactly the same as the area underneath the curve. Okay, this is just something to keep in mind. We have one more thing we're going to talk about. Last thing is going to be an average value of a function. Now, if the function f is integrable and on a closed interval ab, then the average value of the function f on the interval is going to be 1 over b minus a multiplied by the integral of f of x dx from a to b. Okay, so this is just a general formula for you to have. There will be questions asked like this. This is just giving you the average y value of, I'm sorry, it's the average y value of the function in between those bounds. So essentially all you're going to do, you have your lower and upper bounds. So we have 1 over 4 minus 1, and we're going to multiply by the integral of 3x squared minus 2x dx, and we are on the same bounds from 1 to 4. And we're just going to go and work our way through. We're left with 1 over 3 multiplied by the antiderivative. So that's going to be x cubed minus x squared from the bounds of 1 to 4. So we still have 1 over 3. We're going to multiply by, so it's going to be 4 cubed minus 4 squared. And then we're going to subtract f of a, 1 cubed minus 1 squared. We're going to be left with 1/3 multiplied by 64 minus 16 minus 1 minus 1, which is going to leave us with 1/3 multiplied by 48, which gives us 16. So the average y value of this function, so of this function, the average y value in between 1 and 4 is going to be 16. Okay, again, that's just a general formula. So we talked about 3 things today. We talked about the fundamental theorem of calculus, talked about the mean value theorem briefly, we talked about the average value of a function briefly. All 3 of these things are very, very important within the rest of this unit. Okay, so please, please, please make sure you watch this video as many times as you need, ask some questions. We're gonna have office hours tomorrow. Okay, please, please, please. I hope you understand this. Figure it out. Thank you. Have a good one.